and simulation in solar desalination systems. www.redslibrary.com.
Hi everybody, Professor Muhammad Shah with you. Today, our subject today is to talk about how to extract your analysis and available data from a CST model, concentrated solar tower, working on molten salt working fluid. Okay, first of all, you have to after download, you can, this is your model, suppose this is your model, and you can extract it here, suppose. Okay, extract it. You'll find this model. This is your folder. Okay, your model. Okay, let's group our by type. Yes, this is our model SLX. This is our model type. So you can run it by double clicking, or go to your Matlab. Okay, and drive it from your this bus. You can drive it on from this bus by go to your destination folder, and you can just double clicking here, and it will open. Okay, and don't remove any of any content from your folder. Don't remove any of these, even pictures or photos. Don't remove anything. Okay. Let's head back to our model. Okay, your model should be appear like this. We have to simulate. We can adjust our simulation time from the beginning to 0. If you have any intention to work on a fixed point iteration or fixed point run, just for a specific point run, you have to assign this for 0. Okay. And you can assign something if you'd like by double clicking here. Okay, this menu, in this menu, as you can see here, you can adjust some parameters here, such as ambient temperature, solar radiation. Suppose it's 500 watt per meter square. Okay, and this is inlet receiver temperature. This is inlet temperature to the receiver. Okay. Because it's molten salt, we have to not adjust below 150, 200, and so on. 200, quite interesting, to avoid the freezing of the molten salt. This is outlet receiver temperature. We can adjust it at suppose I am going for 400 as a starting. Okay. Absorber cavity efficiency. Okay, it's normally around 0.85, 0.9. Suppose it's 0.8. Okay, and we are going to discover the effect of increasing or decreasing all of these parameters. Mass flow rate. Mass flow rate normally, I think it's around. Suppose it's beginning from 150. Let's see the effect of mass flow rate. And the heliostat mirrors. You can select between some generation of mirror. Suppose I'm going for 4th generation, and this 4th generation will cost around 150 US dollar per meter square. Okay, and this is adjustable inputs. Okay, you have to hit apply. Okay, let's go inside. This is our model briefly. Okay, this is your block model. Double clicking on your block. Okay, or just right click here. Okay, mask. Look under mask or control plus U. This is your model, and these are inputs in between these brackets. And we have here, I'm sorry, these are outputs, and this is function, concentrated solar tower, molten salt, and these are our inputs. So you can add here any parameter, but you have to, or you should use it here within this editable subroutine. This is your subroutine. in order to calculate efficiency, receiver cavity top temperature, some heat transfer coefficients, and the proper analysis should be calculated. And this is a function of molten salt properties such as specific heat capacity, pressure, and so on. Okay, how can we collect our data? We have to, this is our outputs, receiver, cavity temperature, outlet pressure, outlet collector enthalpy, collector thermal power, and thermal power is responsible for this. It's a design model, so we have to calculate from thermal power. We can calculate transportation costs, absorber collector area, absorber costs, total land area, based on our specification. What is the total land area, because it's a design model. It's quite interesting and very important. And what is mirror costs, number of solar heliostates, tower height. Tower heights. What is the tower heights? And from tower heights we can calculate tower cost, field diameter. What is the diameter of the field? What is the distance behind diameter? Distance at the front of the diameter of the field of the tower. Distance behind the tower and distance front of the tower. Cavity height, cavity diameter, tower base diameter, and so on. What is quite interesting and very important, you have to check this. Okay, suppose this is outlet pressure. If you would like to inspect, we have different ways to inspect our outputs or to extract our outputs. The first thing is that we are going to use this stream signal data inspector. It's quite interesting. Okay, therefore we have to check this stream signal, okay, double clicking, and we can write here outlet pressure bar, this unit. Okay, and we have to check this one. It will send this data from here to the data inspector. Okay, and also irreversibility. We can check all of this, okay, at the same time, and go here and select it. Okay, you have to keep watching this visualize signal small square. Okay, and we can write here double clicking and write exergy efficiency. Okay, efficiency. Okay, exergetic efficiency. This is exergy inlet. We can write here exergy inlet in kilowatts. Okay, and many parameters you can extract. Okay, this is radiation in kilowatts, total losses, thermal total losses, and so on. Okay, another type is that you just click on, not double clicking, just one click on this data block and go here for Model Explorer, and you'll find this concentrated solar tower molten salt, and we have to click on the edit block. From here you can check any parameter and you can save the final value to workspace. Okay, I'm selecting pressure, temperature, enthalpy, thermal power, exergetic exergy efficiency of the solar collector. Okay, you can add what you inlet collector efficiency, TCN. It means temperature collector inlet, mass flow rate in collector, total mass flow rate, ambient temperature, solar radiation, and don't forget to hit apply. By checking this, you can find yourself able to collect data or matrix or whatever from here, or to export it to Excel sheets. It's quite interesting. You will find out what we are talking about it. Anyway, okay, we adjusted our inputs. we can simply hit run. Okay, let's simply hit run, as you can see here. Okay, run is finished. I'm sorry. Okay, okay, based on our inputs specified here, we will find out that this is receiver temperature, outlet receiver temperature, outlet pressure of the molten salt, outlet enthalpy of the molten salt. This is the thermal power, reversibility, exergetic efficiency, total exergy N. This cost stream is responsible for if you would like to add exergy economic analysis. It is not interesting here now. Okay, and don't forget this our inputs. Okay, you can check it also. You can check it from here. You can add this one right here, mass flow rate. Okay, kilogram per second. Okay, anyway, now we can these are results: field efficiency, reflector total area, convection heat loss, radiation heat loss, total heat loss. Okay, and we have here these are transportation costs, absorber collector area, absorber costs. Okay, and total land area, mirrors costs, total number of failure states. Okay, total number of failure states. Okay, and these are types. Tower height. This is our tower height. It around 74 meters height, and you can. It's a design model. Okay. Suppose I'm going. If you check, let's go for workspace. Yes, you will find your data here. Okay, these are your data. Okay, because it's a point, not a matrix. Okay. Okay. Another type of data collection is to go for dynamic modeling with respect to time. I have to go here and set my simulation time into infinity. Okay, and let's hit save model. Okay, based on our the same inputs, I'm going to change the input dynamically with time. Okay, and we have here, we have to keep watching our results. Okay, just hit run and keep moving these inputs. Okay, let's hit run first. Okay, as you can see here, the model is trying. Okay, model is going smoothly. Let's go and trying to increasing solar radiation. Okay, increasing solar radiation of per meter square. Okay, increasing up to 8, suppose it up to 800, 900. Okay, and let's increasing inlet receiver temperature and keep watching the effect on collector reversibility rate and okay, up to 250. Okay, exergy, thermal power, this total thermal power. Okay, as well I'm going to increasing the outlet receiver temperature up to 560, 565. Okay, massive energy income to the receiver. Okay, as you can see here. Okay, down to 5. Let's go down in order to watch the effect. Okay, going down again, and the absorber efficiency I will increase it up to 0.9, 90%. Okay, 90%. Okay, and okay, and stop our simulation. Okay, fine. Let's go and this under the case of infinity. Okay, let's go and clicking here and see our data inspector results. What is going on? Okay, this is absorber area. Okay, this is absorber area fluctuation according to your changes, and if you made another run, you will realize here the new data. Okay, this is increasing the solar radiation. Okay, increasing the solar radiation, it's quite useful to your system because it will reduce the absorber area, and this are increasing also the effect of increasing inlet field temperature will reduce the solar field area, and this is the outlet effect of outlet temperature. Okay, and the same effect of outlet temperature increasing and decreasing. As you can see, receiver cavity temperature, okay, outlet pressure, okay, reflectors area, okay, reflectors area, as you can see here, convection, okay, radiation, okay, on the same curve, total losses, okay, and we have here outlet enthalpy. This is the thermal power, massive thermal power, the same effect, okay, exchange efficiency, field efficiency, okay, fluctuating. This is total area, total land area, mass flow rate. Okay, we didn't control mass flow rate actually. We didn't. You can control it. Okay. Okay, it's quite interesting. Let's make another one. That's it. Closing, and we can make another run by changing a different parameter, but at this time I can go here and let's go for the use of dashboard. Suppose I am using half gauge. Let's try with dashboard scope here. Sorry. Okay, dashboard scope. Let's hitting here and we can select thermal. Okay, Q thermal energy, it added well. Okay, hit apply. Okay, limits, it's from 0 up to suppose it's 1E6. Okay, hit apply. This is our range, and let's go for another dashboard. Let's go for half gauge. We can change, we can use suppose I'm going for double clicking here and can select our signal. Suppose it's total land area. Okay, okay, total land area. Okay, you can adjust minimum and 1E6 again, this total land area. Okay, and we can select another type of dashboard. Let's go for tower height. Okay, tower height, let's go for tower height. Go for dashboard again. Okay, tower height here. It's quite interesting, very nice to extract your data based on visual aspects or something like this. The tower height, yes, and limit from minimum 0, maximum to let it be 300 just in case. Okay, okay, but these can work effectively based on infinity of time. Okay, let's hit run and see our result, but we have to double clicking here, turning back and see. Okay, let's hit run and see changing. Let's go for decreasing. I will go for to decrease solar radiation, as you can see here, decreasing solar radiation and decreasing ambient inlet field temperature down to 200. Okay, 200, and decreasing outlet temperature down to 400. Okay, 450. Cavity efficiency, let's decrease down to 0.7. Okay, mass flow rate, let's increase mass flow rate up to 160, 102. Let's go for 250. Okay, okay, again 300, 500. Okay, 500. Okay, let's go for 500. Okay, 400, 500, up to 800. 800. super mass flow rate 800. Okay, let's hit stop and see our results. As you can see here, this is a tower height variation. Okay, as you can see here, and this is your thermal power decreasing and increasing and so on. I will check this, what is the problem with this, but we can return back here and we can add another run on the same figures, as you can see here, and we can export our data. Let's go here and okay, this is the last run. So this is absorber area. Let's go for an add absorber area. So we have, this is the first run, and this is your second run. Okay, a variation based on your receiver temperature, the same. Okay, so we can compare between each run. Okay, reflectors, total area. Okay, changing outlet enthalpy, the same. There's a difference between both. Thermal power, sure, there's a huge difference, because this is mass flow rate effect. It's clearly that it's a changes with massive effect on the process. I'm trying to discover what is the problem with solar field area with this one. Let's remove this, and we can add here half gauge, another half gauge. Let's go and see. Double clicking. Let's go for this signal. Okay, this signal from 0 up to 1E5. Let's hit apply. Okay, that's it. Okay, let's go for here, double clicking, returning back, and let's hit run. Let's hit change. I'm trying to increase solar radiation. Okay, increasing solar radiation and decreasing mass flow rate. Total area 1.1E6. We have to down to 1E5. We have to put ourselves in the range of field area. Okay, that's decreasing down to 300. Okay, total field area 1E5 is quite little, quite few. I'm sorry. Okay, increasing efficiency of the absorber area. Okay, increasing solar radiation. We're still out of the range. I have to increase this. 1E7. Let's try. Let's run again. I'm not sure why it is not working. Increasing again. So this our results, but anyway, we can realize this effect by I will try another let's see it here, and we can add dashboard scope. Let's try this one. Okay, double clicking. Okay, from 0 to 1, make it 2E6. Apply. Let's go and hit run. Let's see change. I'm sorry. I will try to decrease solar radiation. Decreasing solar radiation here, and increasing Yes, there's change here, increasing outlet field temperature. Okay, it works with dashboard scope, increasing mass flow rate, increasing massive effect of mass flow rate on the process. Okay, hit stop. As you can see here, the effect on the total field area that you can collect. So you can go here and you can export your data of so you can select you can export this data to the figure or sorry, yes, you can export going here. Yes, select this one for example and select this, the curve, and export it to M file, to mat file. Suppose it's to mat file. I hit export. You will find it it exported here. Yes, this T out. You can rename it if you would like, and you find your data. Okay. Okay. Let's hit back, and you can here, for example, send to figure. You can send all of these to a figures, or copy all of the plots. You can copy it. It's quite interesting and easy for you to collect your data. And these are the results with respect to time, as you can see here. So yes, we sent our data to figure, so we can handle and control everything here. As you can see, you can control your data. This is the first run and this is your second run. You can add many runs, 4, 3, whatever. Okay, and okay, finally we easily can say that you have a model. You can export your data easily. You can control design analysis for concentrated solar tower. This your model is so useful for your pre-analysis before projects, or suppose you are going to judge about establishing solar field or something like this. So you have some quite interesting inputs. You can control these inputs, like they are very important: mass flow rate, inlet temperature, outlet temperature, in order to discover what is your field or land area that you are going to establish or construct your blend. Finally, we would like to thank you very much for your interest in our models. Don't forget to like, share, subscribe. Thank you very much.